ఇక్కడ పెడతారా? Hello, good afternoon. Am I audible? Is it audible? Yes. Okay. Now let us start today's class. Yesterday, after completion of vector differentiation part, we have started the last subtopic in the calculus, that is vector integration. In the vector integration, we have said what is line integral, what is the surface integral, and started the just line integral only. But yesterday there was a problem with the pen, so we did not continue that one. Now we continue the last class. That is the continuation of the last class only. Here we have started yesterday only, just line integral. If a vector function f bar is defined at every point on the curve C, if a vector function is defined at every point on the curve C, then the evaluation of integral of a vector function f bar along a curve C from a point A to point B is a line integral of vector function f bar, and it is given by integral sign below the integral sign C f bar dot dr bar on. Here C is the path of integration. In space along the given arbitrary path C, we try to evaluate the integral. We are evaluating the integral along the arbitrary path C between 2 points A and B only. So this is a space integral. That is why it is a line integral. It is a space integral. Suppose the curve is along the x-axis or y-axis or z-axis, directly the coordinate integral, which are the same as the definite integrals only. Suppose this curve is along the x-axis from here to here, then that is same as the coordinate integral or ordinary definite integral. Whenever the path is along the x-axis, y-axis, z-axis, line integral and single integral both are same only. The path is in space, then line integral is different from coordinate integral, that is ordinary definite integral only. Because of the curve in space, directly we cannot evaluate the line integral. We try to convert the line integral to ordinary definite integral, that is definite integral only. We try to convert line integral along the curve in space to ordinary definite integral using the equation of the curve, and then we evaluate. Similarly, the surface integral will be evaluated with the help of the double integral. Volume integral will be evaluated with the help of the triple integral. These are the coordinate integrals. These are the space integrals only. It is only difference only. The curve is along the coordinate axis. Line integral and single integral both are same only. The surface of the object is on the coordinate planes. Then surface double integral both are same only, like that only. Here we read this as integral over C f bar dot dr bar. Integral over C f bar dot dr bar only. Now to evaluate this integral using the single integral, we try to express this integral in Cartesian form when the function is given in terms of Cartesian form. That is note point number 1. Line integral in Cartesian form only. If f bar equal to f1 I bar plus f2 j bar plus f3 k bar and dr bar equal to dxi bar plus dyj bar plus dzk bar, where r bar equal to xi bar plus yj bar plus zk bar, then integral over c f bar dot dr bar equal to integral over c. Now f bar dot dr bar, this is a f bar, this is a dr bar. Between these two dot product is written as f1 dx plus f2 dy plus f3 dz only. And then we evaluate integral each integral. The first one is integral with respect to x, second one is integral with respect to y, third one is integral with respect to z only. So whenever function is given in Cartesian form, we try to write this integral, the line integral in this form only. This is the Cartesian form of line integral only. Next, note point number 2. in general, the value of the line integral depends on the path. Depends on path or curve C, but not on endpoints, A and B of the curve C only. We always evaluate integral of the vector function along some curve in space from one point to other point only. Suppose if you are given 2 points in 1D space, the 2 points can be joined only in one way only. If you are given 2 points in 1D space, the 2 points can be joined only in one way only. Suppose the 2 points are given in space, 2D space or 3D space, then the 2 points can be joined by infinitely many ways only. The 2 points can be joined by infinitely many ways only. That is why the value of the line integral depends on the path, not on endpoints A and B only. This is a point only. In general, the value of the line integral depends on only the path by joining the points A and B, but not on endpoints of the curve only. Next, note point 3. If f bar equal to f1 I bar plus f2 j bar plus f3 k bar is an irrotational vector. Irrotation means curl is 0 bar only. Irrotational vector, that is within the brackets del cross f bar equal to 0 bar, or curl f bar equal to 0 bar, or f bar equal to del phi. F bar equal to del phi. If the function is irrotational, then the irrotation can be written as gradient of some scalar function. Then integral over C f bar dot dr bar equal to integral over C. When f bar is irrotational, then f bar will be replaced by this del phi, because every f bar will be written as gradient of scalar function dot dr bar. This is equal to integral a to b del phi dot dr bar is d phi. In the vector differentiation part, already we have written this. We'll go back to this. This from this only, d phi equal to this sum. This sum is same as del phi dot dr bar only. So d phi is same as del phi dot dr bar for this function. We are writing here only. So del phi dot dr bar is same as d phi. Integral of d phi is phi from a to b. This is equal to phi of b minus phi of a only. Phi of b minus phi of a only. When function is rotational, without evaluating the integral, we write the value of this integral by using this function phi. Here the function phi is called scalar potential function. Scalar potential function. The function is irrotational, then we can write the integral value by using this scalar potential function. Because for a given irrotational vector, we can write the scalar potential function. That is the value of the line integral depends on the two endpoints A and B of the curve C, but not on curve C. So whenever the function is irrotational, then the value of the integral depends on only endpoints. Suppose the function is not irrotational, in general, the value of the integral depends on the path. But here, function is irrotational. If it is irrotational, the value of the line integral does not depend on the path, depends on only endpoints. That is why using the scalar potential function and using the limits directly, we get the value of the line integral. It is the advantage on it. Next, note point number 4. Note point number 4. If f bar is a force vector acting on a moving particle in the force field, if a bar is a force vector acting on a moving particle in the force field, then the total work done by the force F bar is then the total work done by the force vector F bar along a curve C from a point capital A to a point capital B is given by line integral. That is work done equal to integral over C F bar dot dr bar. Next, note point number 5. If F bar is an irrotational vector, that is within the brackets del cross F bar equal to 0 bar or curl F bar equal to 0 bar or F bar equal to del phi, then the value of the line integral along a closed curve C is 0. That is integral over C F bar dot dr bar equal to 0. Because of closure curve, on the integral sign we write circle symbol on it. So that is integral over C f bar dot dr bar. Suppose the curve is closed curve. The curve, given curve is closed curve. Then integral value is 0 when the function is irrotational. If the function is irrotational, the curve is closed curve. The value of the integral along the closed curve is always 0. That's all. These are the standard results. Note point 1, 2, 3, 4, 5. Now we do the problems on this. Problem number 1. If f bar equal to 2zi bar plus 2yj bar plus 2xk bar, then the value of the integral, integral over C f bar dot dr bar along the straight line C from 0 to 1 to 4, 1 minus 1 is. We are given vector function f bar, that it is in Cartesian form, and we are asked to find the integral of this vector function along a curve C from one point to other point. Here name of the curve or name of the path is straight line only. Along the straight line between two given points, we have to evaluate the integral on. That it is line integral. Because of the integral over C f bar dot dr bar is line integral on. Okay. Okay, let us do this problem. Let I equal to integral over C f bar dot dr bar. Then I equal to integral a to b, we write the points directly, integral 0 to 1 to 4, 1 minus 1. Inside the integral f1 dx plus f2 dy plus f3 dz only. This is f1, this is f2, this is f3. So line integral in Cartesian form is 2z into dx plus 2y into dy plus 2x into dz. So line integral is written in Cartesian form only. Now we have to evaluate each integral. We have a sum of 3 integrals only. First one is integral of 2z dx. Second one is integral of 2y dy. Third one is integral of 2x dz only. Actually, we have 3 types of integrals. Single integral is also called definite integral or ordinary definite integral. Single integral, ordinary definite integral, all are same. So we have 3 types of integrals: single, double, triple. Single, double, triple. Single is like this: integral x equal to a to b f of x dx, or integral y equal to c to d f of y dy. Integral z equal to a1 to a2 f of z dz, or integral t equal to a to b f of t dt. All these are definite integrals, or all these are ordinary definite integrals only. Now observe all the integrals. This integral is with respect to variable x, function is function of x, and x limits only. Integral is with respect to y, variable limits, here for y variable limits and function of y only. Integral is with respect to z, z limits, function of z. Integral is with respect to t, function of t, t limits only. So whenever it is a with respect to x means it should be function of x. If it is with respect to y, it should be function of y. With respect to z means function of z. With respect to t means function of t only. We have only this type of integrals. We don't have the like this integral of function of some other variable with respect to like this only. We don't have this. We don't have this type of integral till now only. Now see this integral, very first one. Integration is with respect to x, but it is not a function of x only. So we cannot evaluate this only. Second one, Integration is with respect to y, it is function of y. We can integrate this. Integration is with respect to z, it is function of x. So it is not integrable only. So out of 3 integrals, 2 are not integrable, 1 is integrable only. Because of this only, the line integral along a curve in space cannot be evaluated only. The line integral along a arbitrary curve in space cannot be evaluated. That is why we try to convert the line integral to ordinary definite integral or single integral like this. We convert the line integral to one of these only by using equation of curve so that we can evaluate only. Suppose here instead of 2z, here 2x is there and here 2z is there. We can evaluate directly, no problem. But if we have 2z here 2x like this, we cannot evaluate only. In general, line integral cannot be evaluated directly only along a arbitrary curve in space. That is why we try to convert line integral to single integral, one of these single integral only using equation of curve. Already we are given the name of the curve, that is straight line. Using the straight line formula, we write the equation of the curve. The equation of straight line by joining these 2 points is, general formula is x minus x1 by x2 minus x1 equal to y minus y1 by y2 minus y1 equal to, suppose only these 2D straight line. 3D straight line means z minus z1 by z2 minus z1. This is the equation of the straight line using 2-point formula. We have the x1, y1, z1, x2, y2, z2 only. Substitute these in this, which implies x minus x1 divided by x2 minus x1 equal to y minus y1 by y2 minus y1. Next, z minus z1 by z2 minus z1. This is the equation of the straight line. But our aim is converting the integral of 3 variable to integral of single variable with respect to single variable. That is why here we fix one of the variable, we express other 2 variables in terms of x only. Or we fix y, we express other 2 variables in terms of these. Or we fix z, we can add the x and y in terms of z like this. We can keep one and we can express other 2 in terms of that fixed one only. Or we can write the all 3 variables in terms of some other new variable only. Instead of fixing one variable, writing other 2 in terms of one variable, we can express all 3 x, y, z variables in terms of some other variable. Let us suppose that is t. So that we can add x in terms of t, y in terms of t, z in terms of t, and then we can add the integral this form only, so that we can evaluate. We can add the integral in this form. Which implies x equal to the first and last, that is x equal to 4t. Next to y equal to minus t plus 2, 2 minus t, comma z equal to last 2, 1 minus 2t. Which implies dx equal to 4 dt, dy equal to minus dt, dz equal to minus 2 dt. When you are converting x, y, z to t variable, we have to find the t limits on it. To find the t variable limits, we can use any one of these 3 equations on it. Out of 3 equations, we consider the simple equation x equal to 4t only. X equal to 4t. Already we know the x limits. Using x limits, we can find the t limits only. The lower limit for x is 0, upper limit for x is 4. The x limits are same as x coordinates. X limits are same as x coordinates only. If x equal to 0, t is also 0. X equal to 4, t equal to 1. We substitute all these. We substitute all these in this integral only. Now, I equal to integral t equal to 0 to 1 to z, 2 into z, z is this 1 minus 2t into 2, 2 minus 4t into dt, dx, dx means here 4 dt plus 2y, this is y into 2, 4 minus 2t in place of dy minus 1 dt plus 2x. X equal to 4t, 2x is 8t. In place of dz, right, the minus 2 dt. Substitution is computed, which implies I equal to t equal to 0 to 1. Simplify this. Dt is common. Now search for constants t power 1, t power 2 terms like this. Now first we try to find out the constant terms. 2 into 4, 8 minus 4. 8 minus 4, 4 minus. Next t power term minus 16 plus 2 minus 16 plus 2 minus 14 minus 14 minus 16 minus 30. No t square terms, that's all. Equal to. Now observe this. Integral, single variable limits, function of single variable with respect to single variable. This is in the form of like this. This is in the form like this only. We can evaluate directly only. 4t minus 30 t square by 2 from 0 to 1. Directly, therefore I equal to, we can add the value on 4 minus 4t minus 30 by 2 minus 11. It is the answer. This is a 2 marks gate question only. 2 marks gate question. Right? This is a general method of evaluation of any line integral only. We tried the line integral to single integral using equation of curve, and then we try to find the limit. We try to find the value of the integral. It is a general method. But in every problem, the name of the path may not be given only. Name of the path is not given on. Name of the path is given using that path. In this problem, equation is not given. Equation of the curve is not given. But instead of giving the equation of the curve, name of the path is given. Using name of the path, we are writing the straight line equation only. Instead of giving the name, directly equation is given. We can use the equation, we can do the problem. Suppose name of the path is not given. Next, equation of the curve is not given. In such case, we have to check the function is irrotational or not. Whenever equation of the curve is not given or name of the curve is not given, in such case, check the function is irrotational or not. If it is irrotational, we evaluate the problem in easy way by using note point number 3. Right? If it is irrotational, we can add the value of the integral in easy way by using note point number 3 with the help of the scalar potential function by substituting upper limit, lower limit. Suppose the equation is not given, path is not given, the function is not irrotational, we cannot evaluate. That's all. This is a general method, but we can do this problem in other way also. For the same problem, method 2. Method 1 is general method. This method 1 is general method. Now we do the same problem in other method only. Line integral. Now I equal to integral a to b 2z dx 2y dy 2x dx plus 2y dy plus 2x dz on. Here it is a sum of 3 terms. If you are able to write the single term, sum of the 3 terms as a single term, we can go for direct integration. Instead of doing the problem by previous method, we can do the direct integration also. The only problem is here with the first term, last term. Second term is integrable only, but first and last are not integrable only. If you write the 2 terms, first and last together like this, from the first and last 2 is common, z into dx plus x into dz. But these 2 terms will be written as d of xz only, differential of this function xz only. In the differential equation topic, one of the subtopic is first order and first degree differential equation. In the first order first degree differential equation, one of the method is non-exact method. In the non-exact method, there are 5 methods for finding the integrating factors only. Out of 5 methods, last method is inspection method. In the inspection method, like this, we have written the many formulae only, differentials only. So if you write the first and last together, we can write the d of xz. If it is d of xz, directly we can integrate. This is the advantage only. And this is possible when function is rotational only, which implies integral a to b 2 into z dx plus x dz plus 2y dy, which implies I equal to integral a to b 2 into d of xz plus 2y dy. Now both are integrable. This integration is with respect to y, it is a function of y. This integration is with respect to xz, function of xz is 1. So we can do the integration. I equal to 2 into integral of 1 with respect to xz is xz plus 2 into integral of y with respect to y is y square by 2 from the points are 0 to 1, 4, 1 minus 1, 4, 1 minus 1. Therefore, I equal to substitute upper limit, lower limit, that is minus lower limit equal to, finally we get the minus 11. It is the answer. For upper limit, x equal to 4, y equal to 1, z equal to minus 1. For lower limit, x equal to 0, y equal to 2, z equal to 1. Like this, we can substitute on it. And this function is called here scalar potential function. So when you compare this method with the previous method, this method will be simple. So this simple method is possible when the function is irrotational. So the function is irrotational, we can go for direct integration like this only. So for given irrotational like this, we can find the scalar potential function and then we substitute upper limit, lower limit. This will give the required answer only. So most of our gate questions are like this only. Most of the gate questions are like this only. It is a 2 marks problem. So instead of doing the problem by previous general method, we can do in this way only. Okay, right. Next, problem number 2. If f bar equal to 2xy plus z cube into I bar plus x square into j bar plus 3xz square into k bar is a force vector, then the work done by the force F bar in moving an object in the force field from 1 minus 2 1 2 3 1 comma 4 comma is. So in this problem, we are asked to find the work done. Finding the work done is same as line integral. We are given force vector. We have to find the work done between these two positions. So again, like previous problem, we can do this problem. Finding the work done is same as line integral. Work done equal to integral 1 minus 2 1 2 3 1 4 f1 dx. This x 2xy plus z cube into dx plus x square into dy plus 3xz square into dz. So work done is given by line integral. Like previous problem here, it is a function of three variables with respect to x. We cannot integrate it. Function of single variable with respect to other variable y. We cannot integrate it. We cannot integrate. All three terms cannot be evaluated directly. So in this case, again, we try to convert the line integral to single integral. But before converting the line integral to single integral, just observe the three terms and check the three terms are written in the form of single term or not. That is d of something or not. If you are able to write the three terms as a single term, then we can go for direct integration only. And also remember the, just observe the given data. In this given data, we are asked to find the work done between these two positions. The path is not given. Equation of the curve is not given. Name of the curve is not given. So in this, for this type of problems, we have to check the function is irrotational or not. To check the function is irrotational or not, we have to calculate curl. If it is 0 bar, irrotational, then exact differential is possible. But without finding the curl also, directly just observe these three terms only. If you are able to write the three terms as a single term, we can go for direct integration. If you are able to write means indirectly that function is irrotational only, which equal, this is equal to integral a to b. If you write these two together, 2xy dx, all these are in terms of x and y. Next we search for another term in terms of xy plus x square dy. X square differential is 2x dx only. Y differential is dy. So it is in the form of d of x square y like this. Next here this term and this term only. These two terms. Z cube dx plus 3xz square dz. Z cube differential is 3z square dz only, and x differential is dx. It is in the form of d of xz cube only. So differential is possible. That is why the given function is irrotational directly on. 2xy dx plus x square dy. These two together plus z cube dx plus 3xz square dz, which implies integral a to b d of x square y plus d of xz cube, or we can add the integral a to b from both d of single function x square y plus xz cube only. 1. Here integration is with respect to this variable. Function of this is 1. We can do the direct integration. This is equal to x square y plus xz cube from 1 minus 2 1 2 3 1 4. This is the answer. So this simple method will be possible. This simple method will be possible when the function is irrotational. That is, the function is irrotational, then exact differential is possible. Then we can go for direct integration on that. Okay. Now in the first problem, the curve is straight line, not a closed curve. In this problem, we are given 2 points. When you are given 2 points and these 2 points are not same, means it is not a closed curve. When the curve is not a closed curve, to find the line integral, we do like this only. Like in first problem, second problem. Suppose the curve is closed, we never do the problem like this. Whenever the curve is closed, we do the same problem in easy way by using Green's theorem. That is the advantage of the Green's theorem. So Green's theorem is used to evaluate the line integral when the curve is closed. Next, Green's theorem. in a plane. Now, Green's theorem is one type transformation which converts line integral to double integral or double integral to line integral only. Line integral equal to double integral only. The statement of this. If capital R is a closed region of xy plane bounded by one or more simple curves. Simple means like this. No self intersection. This is not a simple curve only. This is simple curve only. Simple curve means the curve does not cross itself only. The curve crosses itself. It is not a simple curve only. Throughout our discussion, we consider only simple curves only. Closure means simple closure curve. So bounded by one or more simple curves C and m of x comma y comma n of x comma y comma dou m by dou y and dou n by dou x are continuous functions in a region R. In a region R, then integral over C on the integral sign circle symbol inside the integral m dx plus n dy equal to double integral over R dou n by dou x equal to, sorry, not equal, this is minus dou m by dou y. Dou n by dou x minus dou m by dou y dx dy. This is the relation. So Green's theorem gives the relation between line integral and double integral only. R is a closed region of xy plane bounded by one or more simple curves only. Then the value of the line integral along a closed curve, the value of the line integral along a closed curve is also same as double integral over the plane region. Double integral over the plane region only. So if you are asked to find this line integral, we can write the line integral in terms of double and we write the value of the integral using double integral. So sometimes the evaluation of the line integral using double integral will be simple only. That is why we are using this theorem. Especially we use this theorem only for closure curves. If it is not a closure curve, this is not applicable on it. Okay, let us do the problems on this. Problem number 1. The value of integral of x plus y dx plus x square dy, comma, where capital R is the triangle with vertices at 0 0 comma 2 comma 0 and 2 comma 4 is, it is a given integral. This integral is in terms of only two variables x and y with respect to x with respect to y. So it is a 2D line integral only. First of all, the integral in Cartesian form is f1 dx plus f2 dy plus f3 dz. It is an integral over C f bar dot dr bar. Line integral in Cartesian form, but in terms of three variable, that is 3D only. If it is 2D, integral over C f bar dot dr bar equal to integral over C f1 dx plus f2 dy. 2D means it is a function of x and y dx, function of x and y dy. It is also same as integral m dx plus n dy on. So our given integral is in the form of like this only. So we are given line integral in Cartesian form, that in 2D on. And we are asked to find the integral over the region R, where R is a triangle with vertices like this. Okay. Here, to evaluate this integral, we try to convert the integral to double integral, this given line integral to double integral. After that, we try to find the limits and then we evaluate only. Already we know the method of evaluation of double integral and method of finding the limits of the integral only. Okay. Here this integral over R. The value of this integral over R, where R is a triangular region only. Because a triangular region, its boundary is closed. Because a closed curve, we try to evaluate this integral by converting line to double only using Green's theorem only. By Green's theorem, we have integral over C m dx plus n dy equal to double integral over R dou n by dou x minus dou m by dou y dx dy. Because of closed curve and line integral, we are using the Green's theorem only. Now write the given integral in the form of this left hand side, and we convert the left hand side to right hand side only. That is line to double integral. Now the given integral. So this is not R, this is only C only. Integral over C only. Integral over C x plus y dx plus x square dy equal to. We compare the given integral. We compare the given integral with this general transformation. Find m n, substitute m and n on right hand side only. The coefficient of dy is n equal to x square. Coefficient of dx is m. Dou by dou x of on right hand side in place of n x square minus dou by dou y of m equal to x plus y dx dy, which implies integral over C x plus y dx plus x square dy equal to double integral over R 2x minus 1 dx dy. Conversion of line integral to double integral is completed. Now we write the value of this line integral with the help of this double integral only, because the value of this line is same as value of this double integral only. Already we know the method of evaluation of this double integral. To evaluate the integral, we require the limits. The limits of the integral are not given. The region of integration is given. The region of integration is triangular region only. Zero zero A 2 0 B 2 comma 4. This height is 4 only. This height is 4. This is a line at x equal to 2 only. It is a line at x equal to 2. It is a line at x equal to 0. Next, it is a line at y equal to 0. This is a line at y equal to 4. It is a closed curve and region R. The integral along the closed curve is same as double integral over the region only. The integral over the region is same as integral along the closed curve only. And the equation of this curve is y equal to 2x. Y equal to 2x only. By using 2-point formula, if you write the equation of the curve, this is a closed curve. Up to your drawing the region is completed, we can find the limits by drawing a line parallel to y-axis or parallel to x-axis. In 2 ways, we can find the limits. Let us draw a line parallel to y-axis only. Just below the diagram, we are starting at some point and we are moving like this parallel to axis. When you move like this parallel to axis, the line enters the region through this curve. So this is entering curve. The same line passes through region and leaves the region through this. This is a line L. This entering curve will give the lower limit of y, and this leaving curve will give the upper limit of y. Like this, we can draw the lines from x equal to 0 to x equal to 2. So x will vary from 0 to 2. Then y will vary from y equal to 0. The equation of entering curve is y equal to 0. So lower limit is y equal to 0. Equation of leaving curve is y equal to 2x. This is y equal to 2x. Like this, we can find the limits. Now here we are the limits. Integral x equal to 0 to 2. Integral y equal to 0 to 2x, 2x minus 1 dy, and then dx equal to. Integral x equal to 0 to 2, 2x minus 1 is, line is parallel to y, then we should start the integration with y because variable limits for y on y 0 to 2x dx equal to integral x equal to 0 to 2, 2x minus 1 into 2x minus 0. The double integral is reduced to single. We can add the integral value of this. 2 to 4x square. Integral is 4x cubed by 3 minus 2x square by 2 from 0 to 2. Therefore, integral over c x plus y dx plus x square dy equal to 4 by 3 into 8 minus 2 by 2 into 4. This is equal to value. So it is a method of evaluation. Whenever the curve is given, but here in the question, this may not be given as C. This is understood that we are given line integral and the R is the triangular region only. So it is understood that integral over C, that is C is the boundary of this region R. Next, problem number 2. The value of the line integral integral of 2x minus 1 dx plus x plus 3y dy over the ellipse x square plus 4y square equal to 4 is. So again, we are given line integral in Cartesian form, integral over c f1 dx plus f2 dy form only, and we are asked to find the integral over the ellipse. Equation of ellipse is given. So this ellipse is closed region. So its boundary is closed. So we write the value of the line integral using Green's theorem by converting line to double. By Green's theorem, we have integral over C m dx plus n dy equal to double integral over R dou n by dou x minus dou m by dou y dx dy. Now our given integral over C 2x minus 1 dx plus x plus 3y dy equal to double integral over R dou by dou x of x plus 3y minus dou by dou y of 2x minus 1 dx dy. This is equal to double integral over R x with respect 1, 3y with respect to x 0. So 1, 2x minus 1 with respect to y is, that is here 0 minus 1. 2x minus x plus 3y, x plus 3y, 2x, this is y on. This is minus 1. 1 minus a minus plus 2. 2 is constant, we write outside double integral over 1 dx dy, comma, where R is a ellipse region only. This is given by x square by 2 square plus y square by 1 square equal to 1. Over this ellipse region, we have to evaluate the integral only. Already we know the method of finding the limits here. I will show you how to find the limits of this ellipse region. A square, this here a equal to 2 is greater than b equal to 1. So major axis is x axis only. This is 2. Here x equal to 2. This is x equal to minus 2. And the equation of this ellipse is x square plus 4y square equal to 4. Now the region is starting from x equal to minus 2 and ending with the region x equal to 2 only. The region is lying between these two lines only. Minus 2 to plus 2. For any value of x, we draw the line parallel to y-axis and then we try to find the limits only. Just below the diagram, we start at some point and we move like this. When you draw the line parallel to axis, the line enters the region through this curve. The same lines leaving the region through this curve only. The entering curve will give the lower limit. This entering curve will give the lower limit. The leaving curve will give the upper limit of y. Like this, we can draw the lines from x equal to minus 2 to x equal to plus 2. X limits are like this one. Now from this equation of the curve, write the y in terms of other. Here, if you write the 4y square equal to 4 minus x square, then y square equal to 4 minus x square by 4, then y equal to plus or minus 1 by 2 into under root of 4 minus x square only. But this entering curve is lying below the x-axis. Entering curve is lying below the x-axis. Leaving curve is lying above the x-axis. Below the x-axis, the curve is negative. Above the x-axis, y is positive only. That is why we should take here y equal to plus under root of 4 minus x square divided by 2. Here y equal to minus 1 by 2 into under root of 4 minus x square. Like this we can find the limits only and we can evaluate. It is a method only. But here without using the limits, we can write the value of the integral in easy way. That is the advantage of the double integral. It is advantage of the double integral. Now see this. In the multiple integral topic, already I told you that inside the double integral function is 1, that is same as area of the region. Inside the double integral function is 1, that is same as volume of the region only. Here within the double integral function is 1, because of 1 this is the area only, area of this given region only. But R is the ellipse region. Without evaluating the integral using limits, we write the value directly like this. See this, 2 into area of this ellipse is pi a b, a equal to 2, b equal to 1, so 4 pi. That's area of the ellipse is this. Whenever the function is 1 inside the double integral, without evaluating the integral using limits, then we write the value of the integral with the help of area of the given region only. Using these limits also, if we evaluate, we can get same answer only. You can try for this also. It is the advantage of the double integral. Next, problem number 3. If a bar equal to del phi, then the value of integral over c a bar dot dr bar, comma, where c is x square by 4 plus y square by 9 equal to 1, comma, is. We are given the line integral and we are asked to find this line integral along this ellipse region, along the boundary of this ellipse region. We are asked to find this line integral along the boundary of this. So finally, it is a closed region, its boundary is closed, so C is a closed curve because of this ellipse region only. Whenever the curve is closed, we can evaluate the integral using Green's theorem. But here vector function is not given directly, indirectly given that a bar equal del phi. Given that a bar equal to del phi. If any vector is written as gradient of scalar function, from this we can say that f bar is irrotational, which implies a bar is an irrotational. A bar is an irrotational. If it is irrotational, the line integral along the closure curve is 0 directly, according to last node point in the line integral. Integral over C a bar dot dr bar equal to 0. That's it. From the given this a bar equal to del phi, we can set a bar is irrotational. If it is irrotational, line integral value along the closure curve is 0 always. That's it. It is about line integral. So we have done the line integral problems using Green's theorem without theorem only. Generally, we apply Green's theorem when the curve is closed. The curve is not a closed curve, then we should evaluate the line integral by using normal integration method. That is just like first two problems before the Green's theorem only, before the Green's theorem. Next, surface integral. If a vector function f bar is defined at every point on the surface. Yes, on the surface, yes. Then the evaluation of integral of a vector function f bar over the surface S in space is a surface integral of f bar over S, and it is given by two integral sign below the integral sign S, inside the integral f bar dot n bar ds, or integral over S f bar dot n bar ds. Sometimes this will be written like this only, or double integral over S f bar dot ds bar, since ds bar equal to n bar ds only. Okay. Now, just like line integral, this surface integral will not be evaluated over the arbitrary surface in space directly. Line integral cannot be evaluated in space along the arbitrary curve directly only. We try to convert the line integral to single integral using the equation of the curve only. Like that here, the surface integral cannot be evaluated directly. Again, we try to convert the surface integral to double integral by projecting the surface onto one of the coordinate plane only. So line integral will be evaluated by single integral. In the same way, surface integral will be evaluated by using double integral. Note point 1. Surface integral in Cartesian form. If f bar equal to f1 I bar plus f2 j bar plus f3 k bar, then double integral over s f bar dot double integral over s f bar dot n bar ds equal to double integral over s inside this f1 dy dz plus f2 dx dz plus f3 dx dy. This is just like line integral in Cartesian form only. The line integral in Cartesian form is integral over c f1 dx plus f2 dy plus f3 dz. It is a line integral in Cartesian form. Like this, it is a surface integral in Cartesian form only. Method of evaluation of surface integral. Surface integral can be evaluated using double integral by projecting the given surface of the object onto one of the coordinate plane. So surface integral will be evaluated using the double integral by projecting the given surface of the object onto one of the coordinate plane only. Suppose the surface is projected onto xy plane, then we get some plane region on the xy plane, that is, let us suppose R1. So if R1 is the projection, if R1 is a projection of surface S onto xy plane, then double integral over S f bar dot n bar ds is equal to double integral over R1 f bar dot n bar on xy plane. In place of ds, it will be written as dx dy divided by modulus of n bar dot. Try to remember this like this. Our projection is on xy plane. On xy plane, no z only. So in place of that, here k bar, like this, remember only. So to remember this transformation. With the help of the projection, we convert the surface to double, and using double integral, we get the value of the surface integral only. Because surface integral directly cannot be evaluated, like that line only. Next, second point. If R2 is the projection of surface S onto xz plane, then double integral over S f bar dot n bar ds equal to double integral over R2 f bar dot n bar. Our projection is on to xz plane. In place of ds, we write this as dx dz divided by modulus of n bar dot on xz plane no y. So in place of y here we remember this as j bar. Next, third point. If R3 is the projection of surface S onto YZ plane, then double integral over S F bar dot N bar ds equal to double integral over R3 F bar dot N bar on YZ plane, no X. So on YZ plane, we write the ds as dy dz divided by modulus of N bar dot, here I bar in place of X. Just like line integral to single integral using equation of curve, here we convert the surface to double integral using the projection only. And then we write the value. In the case of line integral, the curve is closed curve. In the case of line integral, curve is closed curve. We write the value of the line integral in easy way by converting line to double according to Green's theorem only. So whenever line integral is given, we check the curve is closed or not. Not closed, we evaluate line integral by using line to single integral conversion only. Suppose the curve is closed, we evaluate the line integral using the Green's theorem. Like that, for the evaluation of surface integral, we check the surface is closed surface or not closed surface only. If it is closed surface or open surface, again we have simple method for the evaluation of the surface integral. The simple method is here theorems, using theorems only. If it is a closed surface, we write the value of the surface integral using the Gauss divergence theorem. If it is open surface, using the Stokes theorem, we write the value of the surface integral. That is the advantage only. Otherwise, if you do the surface integral by using the surface integral method, it will take more time. So to reduce the time, in easy way to evaluate the surface integral, we use one of the theorem, either Gauss or Stokes, that depends on the object surface only. Now next, we go to next page. Gauss divergence theorem. Now this theorem gives the relation between surface integral and volume integral only. This theorem gives the relation between surface integral and volume integral. If you are asked to find the surface integral over the closed surface, we convert the surface integral to volume integral. In easy way, we can add the value of the surface integral with the help of volume integral. It is the advantage of the Gauss divergence theorem, just like Green's theorem for line integral along the closed curve. Now we read the statement of this. If S is a closed surface, S is a closed surface enclosing, S is a closed surface enclosing volume V of the region and F bar, or if we have a volume region that is bounded by the closed surface S, any one. F bar equal to F1 I bar plus F2 J bar plus F3 K bar. Is a vector defined and differentiable at every point on the region V, then double integral over S on the integral sign circle symbol, because closed surface only. F bar dot N bar ds equal to triple integral over V div F bar dv on. That's it. Is a transformation. Surface integral to volume integral to surface integral, according to this theorem, comma, where N bar is outward drawn unit normal vector to the surface S, where N bar is outward drawn unit normal vector to the surface S. In the surface integral also same. For this surface integral also, N bar is the unit normal vector to the surface in outward direction only. Next, theorem number 5, Stokes theorem. And this theorem converts the line integral to surface integral, or surface integral to line integral. Statement. If S is an open two-sided If S is an open two-sided surface, bounded by simple closed curve C and F bar equal to F1 I bar plus F2 J bar plus F3 K bar. Is a vector defined and differentiable at every point on the surface S, then integral over C F bar dot dr bar equal to double integral over S curl F bar dot n bar ds. Comma, where n bar is outward drawn unit normal vector to the surface S, where n bar is outward drawn unit normal vector to the surface S. Now this Stokes theorem is applicable when the surface is open two-sided surface. Gauss divergence theorem is applicable when surface is closed. So if you are given surface integral, then you have to check the surface of the object is closed surface or open surface. Open surface, evaluate it by using Stokes theorem. If it is closed surface, evaluate the problem by using Gauss divergence theorem only. If you are given line integral along a closed curve, then we evaluate by using Green's theorem, right? Next problems on this. The first problem. The value of double integral over S F bar dot n bar ds, comma, where S is the surface of the sphere x square plus y square plus z square equal to 16 and F bar equal to xi bar plus y j bar plus z k bar, comma, is. Now check whether the given integral is line integral or surface integral only. But we are given the surface integral. From this we can say surface integral, or from this word surface we can say that it is a surface integral. If it is a surface integral, check the object. What is the name of the object? The name of the object is sphere. And the equation of the sphere is x square plus y square plus z square equal to 16. And we are not given any condition on the surface of the sphere. In the problem, condition is not given on the surface of the sphere. Condition means above the xy plane, below the xy plane, left of the yz plane, right of the yz plane, like this, upper half of the surface, lower half of the surface, like this only. In first talk, 10 to second on. We are not given any condition on the surface of the sphere. So from this we can say The surface of the sphere is closed surface only. You have to consider the total surface of the sphere. Because the total surface of the sphere, it is a closed surface. Because of the closed surface of the object, we evaluate this problem by using Gauss divergence theorem only. Right, in the solution. Because the closed surface object, we evaluate it by using Gauss divergence theorem only. So first we have the Gauss divergence theorem transformation. By Gauss divergence theorem, we have double integral over S on the integral sign circle symbol inside the integral f bar dot n bar ds equal to triple integral over V div f bar dv only. Just like Green's theorem only. Integral over c m dx plus n dy equal to double integral over r dou n by dou x minus dou m by dou y dx dy only. This is the Green's theorem. This is the Gauss divergence theorem only. To write the value of the line integral, we write the value of this line integral using the double integral only with the help of the Green's theorem. Like that here, to write the value of the value of this surface integral, we write the value of this by using this triple integral, this volume integral only, according to this Gauss divergence theorem only. So we are given surface integral only. We try to convert the given surface to volume integral. With the help of triple, we write the value of this only. Now, double integral over S f bar dot n bar ds equal to triple integral over V. Divergence is already we know the method of finding the divergence. The divergence formula is dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z dx dy dz equal to triple integral over V f1 f2 f3. f1 with respect to x is 1. This is equal to f1 with respect to x is 1 plus f2 with respect to y is 1 plus f3 with respect to z is 1 dx dy dz equal to 1 plus 1 plus 1, that is 3, constant right outside, triple integral over V 1 dx dy dz. This is just like the second problem in the Green's theorem. In the second problem in the Green's theorem, within the double integral, function was 1. Like that here, in the triple integral, function is 1. Whenever function is 1 inside the triple integral, this value is same as volume of the given region only. Our object is sphere. Without evaluating this integral using limits, we write the value of this integral with the help of the volume of the sphere formula. That is the advantage of the theorems only. 3 into the volume of the sphere is 4 pi by 3 into r cube, r equal to the radius 4. 3 get cancelled, 4 pi into 4 power 3. Therefore, double integral over S f bar dot n bar ds equal to 256 pi. It is the advantage of the Gauss divergence theorem only. If you don't have this theorem, then using the surface integral, you have to evaluate it. Using surface means converting surface to double and you have to evaluate it. It takes more time only. So this is a simple method. Next, problem number 2. Let f bar equal to x square plus y z into I bar plus y square plus xz into I bar, so j bar plus z square plus xy into k bar be the differentiable vector point function full stop. Then the value of integral over C f bar dot dr bar, comma, where C is the curve x square plus y square equal to 4, comma, z equal to 2, comma, is. Now read the problem. The value of integral over C f bar dot dr bar is required on. So we are given line integral and C is the curve x square plus y square equal to 4. It is the equation of the circle and no condition on the circle means it is a closed curve. Whenever line integral is given along the closed curve, we can evaluate the integral by using Green's theorem. We know that one. Here also line integral is given, closed curve is given, but one difference is there. For line integral along a closed curve, we have two theorems. One is Green's theorem and Stokes theorem. Green's theorem and Stokes theorem both are same. The Stokes theorem is the extension of Green's theorem. Stokes theorem is the extension of Green's theorem. Green's theorem, in the Green's theorem statement, we have written like this name, Green's theorem in a plane. Green's theorem in a plane. Plane means 2D only. So Green's theorem is for two-dimensional object. Stokes theorem is for three-dimensional object. Otherwise, both are same only. That is why Stokes is the extension of Green's theorem only. So whenever line integral is given along a closed curve, check the object is 2D object or 3D object. Just observe the given object. Our given object is 2D object or 3D object, check it only. Suppose the given object is 2D object, evaluate it by using Green's theorem. The given object is 3D object, evaluate it using Stokes theorem. It is the advantage. That's so whenever line integral is given along a closed curve, check the object is 2D object or 3D object. If it is 2D object, Green's theorem. If it is 3D object, then Stokes theorem. In this problem, we are given 3D object because of this. Z equal to 2 only. Not only just x square plus y square equal to 4. Suppose this z equal to, this is not given. Z equal to is not given. If you are given x square plus y square equal to 4, it is a circular region on xy plane. It is a 2D object. If 2D is a 2D object, we apply the Green's theorem. But this is given along with z equal to 2 only. The meaning of this is we are given circular region at a z equal to 2 level, right? First, what is the equation of the xy plane? Equation of the xy plane is z equal to 0, right? Like that. Here z equal to 2 is the one plane at a height 2 only, parallel to z equal to 0 only. That is like this. Y, x, z. XY plane is z equal to 0 only. Parallel to this, z equal to 2 only. So we are given circular region in the space at a level z equal to 2 only. This is the z equal to 2 only. The equation of the curve is x square plus y square equal to 4 only. It is the surface of the object. We are given circular disk at a level z equal to 2, or on the z equal to 2 plane, we are given circular region only. Or otherwise, our region is the intersection of circular region and this z equal to 2 plane only. The common region of these two only, z equal to 2 and x square plus y square equal to 4 only. That is same as the on the z equal plane, this is the region only. Our object is in space. It is not on xy plane, it is in space only. Because of it is in space, it is a 3D object. That is why we evaluate it by using Stokes theorem only. So we write the Stokes theorem transformation. By Stokes theorem, we have integral over C f bar dot dr bar equal to double integral over S curl f bar dot n bar ds. So to evaluate this line integral, we try to convert the line to surface. Again, for the evaluation of surface, we convert the surface to double with the help of projection. So first of all, to convert line to surface integral, to convert the left to right, left hand side line integral to right hand side surface integral, on right hand side we require the curl of given vector function, curl of this vector function. After that we find the n bar. Now we try to evaluate the curl. That is del cross f bar equal to I bar, j bar, k bar. Dou by dou x, dou by dou y, dou by dou z. F1 is x square plus yz. F2 is y square plus xz. Next, z square plus xy. Which implies del cross f bar equal to I bar into dou by dou y of this function with respect to y is x minus dou by dou z of this function, that is x, into I bar minus with respect to x y with respect to z y j bar plus k bar into with respect to x z with respect to y z into k bar. This is equal to del cross f bar equal to 0 bar. When curl is 0 bar, function is irrotational, which implies f bar is an irrotational. Because of irrotation and closure curve, the value of the line integral along the closure curve is 0. Therefore, integral over C f bar dot dr bar equal to double integral over S in place of curl 0 bar dot n bar ds equal to, if we find the dot product of any vector with a 0 vector, that is 0 only. Double integral over S 0 ds equal to 0. That's all. This is the advantage of the Stokes theorem. Next, problem number 3. The value of the surface integral double integral over S xy dy dz plus yz dz dx plus zx plus dx dy, where S is here dz plus dx, after this zx into dx dy, comma, where S is the surface bounded by x equal to 0, comma, x equal to 4, comma, y equal to 3, comma, y equal to, so y equal to 0, comma, y equal to 3, comma, z equal to 0 and z equal to 4, comma, is. From this we can set surface integral. We are given surface integral, or from this we can say that surface, your name is already given, surface integral. Even the name is not given, this integral is not given, from this also we can set surface integral. So value of the surface integral is required. Whenever surface integral is given, first observe the given object. Check the object is closed surface object or open surface object. Here the object is given by these 1, 2, 3, 4, 5, 6 planes only. That is x equal 0 to x equal 4. These two are parallel planes only. Y equal 0 to y equal 3. These two are parallel planes. Z equal 0 to z equal 4 parallel planes. That is, we are given cuboid with all 6 faces only. Cuboid is our object with all 6 faces. Suppose same cuboid is given with any one face is not given. Cuboid is given with only 5 faces. In such case, that is open surface object. We can write the value by using Stokes. But here cuboid is the object and 6 faces are given. That is why it is a closed surface object, and we try to evaluate this by using Gauss. By Gauss divergence theorem, we have double integral over S f bar dot n bar ds equal to double integral over V div f bar dv. Now we convert our given surface integral. Double integral over S f bar dot n bar ds. In this problem, the vector function is not given directly only, but vector function is given indirectly because the surface integral is given in the form of Cartesian form. f1 dy dz, f2 dz dx, f3 dx dy. The problem is given, that is surface integral is given in the form of Cartesian form. So from this we can get the f1, f2, f3, and we find the divergence only. Triple integral over v dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z dx dy dz. And here the object is cuboid. Whenever object is cuboid, the integral limits are constants only. Because the integral limits are constants, we can do the integration in any order. We can start with x, or we can start with y, or we can start with z, any one of the variable. I am writing the one of the order x equal to 0 to 4. Inside this integral y equal to 0 to 3. Inside this integral z equal to 0 to 4. f1 with respect to x is y, f2 with respect to y is z, f3 with respect to z is x. This is a function dz, dy, and then dx, which implies double integral over s f bar dot n bar ds. Integral x equal to 0 to 4, integral y equal to 0 to 3. Now integrate inner integral with respect to z. Y z, z square by 2 plus xz from 0 to 4 dy, and then dx equal to integral x equal to 0 to 4. Now these are the limits 0 to 4 for z variable. Write the z equal to 4 and integrate directly with respect to y. Because lower limit is 0, directly we write the 4 in place of z, integrate with respect to y directly on. Instead of writing one more step. For y, after substituting z equal to 4, the first term will be 4y, and y integral is y square by 2 plus 16 by 2, 8y plus xz 4xy. Because z is 4, x is constant, 4 is constant, integral of 1 with respect to y is y from 0 to 3 dx, which implies double integral over s f bar dot n bar ds equal to, again lower limit is 0, upper limit is 3. This 3 is for variable y. In place of y, write the 3 and then integrate with respect to x directly. 2, 9, 18. Integral with respect to x is 18x. 8, 3, 24 x plus, in place of y, 3, 4, 3, 12. 12 x square by 2 from 0 to 4. Therefore, double integral over s f bar dot n bar ds equal to, lower limit is 0, upper limit is 4. If you simplify this, this will be 264. Right, like this we can do the problem by Gauss divergence theorem because of the closed surface object. Next, problem number 4. Evaluate the integral over C f bar dot dr bar, where C is the boundary of the upper of surface of the sphere x square plus y square plus z square equal to 1 above the xy plane and f bar equal to 2x minus y into I bar plus minus y z square into j bar plus minus y square z into k bar. So it is a line integral. From this we can set line integral. We are asked to find the integral over C f bar dot dr bar. From this we can set line integral, but surface OD is also given. From this we can set line integral, but in the same problem surface OD is given. So in this problem we have both line integral and surface word. So whenever in a single problem if we can find both surface and line, then this will be surface and line integral problem. It is surface and line integral problem. The surface and line integral both will be given only in one relation. Green's theorem gives the relation between line and double integral. The Gauss-Divergence theorem gives relation between surface and volume. The only Stokes theorem gives the relation between line and surface. So in a single problem, if we can find both line and surface, then this is for, that is we can evaluate this by Stokes theorem only. We can evaluate this integral by Stokes theorem only. By Stokes theorem, or we can say that other way also. The name of the object is sphere, and check any condition is given on the surface of the sphere or not. C is the boundary of upper half of the surface. C is the boundary of the upper half of the surface of the sphere above the xy plane. That is, we are given the some condition on the surface of the sphere. We are asked to choose a surface of the sphere just above the xy plane. That is only upper half of the surface in the xy plane. Above the xy plane, whatever we have the curved surface, that is same as the semisphere half of the, just like cap like this. Only this cap, just like cap only. Or reverse bowl. This object is same as reverse bowl only. So we are given only this curved surface above the xy plane only. So it is an open surface object only. First of all, Stokes theorem is applicable for only open surfaces only. Open two-sided surface means like this. Spoon is an open surface object. This is inner surface, this is outer surface only. Bowl, inner surface, outer surface. Cap, inner surface, outer surface only. Next, This top surface is open for the box like this. All these are open two-sided surface only. For any object, if you are able to see the inner surface, outer surface, if you are able to see the inner surface, outer surface for any object, such a surface is called two-sided open surface only. This also cup, mug, jug, cup, mug, jug, inner, outer, inner, outer, inner, outer. For any object, if you are able to see the inner surface, outer surface, then such surfaces are called two-sided open surface only. So we are given the just like this cap or reverse bowl open surface only. That is why we try to evaluate the integral using Stokes theorem. For this open surface, the line integral along this boundary, the line integral along this boundary equal to surface integral over the surface only. Line integral along this boundary equal to surface integral over the surface. Line integral over the surface equal to surface integral over the surface equal to line integral along this boundary only, right? Or the work done along this boundary is same as flux across the surface only. It is a relation between line integral and surface. That means work done along the boundary is same as a flux across the surface only. Now we do the problem. By Stokes theorem, we evaluate the integral only. First we write the transformation. By Stokes theorem, we have integral over C f bar dot dr bar equal to double integral over S curl f bar dot n bar ds. To convert line to surface integral, on right hand side we require the curl of given vector function. So let us find the curl first. I bar, j bar, k bar, dou by dou x, dou by dou y, dou by dou z. Next, f1 is 2x minus y, f2 is minus y z square, f3 is minus y square z. Now with respect to y, minus 2y with respect to minus 2y z minus with respect to z is minus minus plus 2y z into I bar minus j bar into with respect to x 0 minus with respect to z 0 plus k bar into with respect to x 0 with respect to y minus minus plus into k bar. So which implies curl f bar equal to just k bar. And this is not equal to 0 bar like in second problem. In second problem, curl is 0 bar. That is why we stop here only. We write directly the value as 0 only. But in this problem, curl is not equal to 0 bar. So this is not equal to 0 bar means next we require the n bar. But n bar is unit normal vector to the surface in outward direction. Our given equation of the surface is x square plus y square plus z square equal to 1. For this equation of the surface, we need to find the normal vector and unit normal vector. From the previous topic, out of three quantities gradient divergence curl, one of the quantity gradient gives normal to surface. Using that, we write the unit normal vector. Our object is like this. At any point on the surface, the unit normal vector is given by n bar equal to del phi by modulus of del phi only. N bar equal to del phi by modulus of del phi. Right? This is boundary C. The line integral along this boundary is equal to surface integral over the surface of the sphere. Let phi equal to x square plus y square plus z square minus 1 equal to 0 be the equation of surface S. Then n bar equal to del phi by modulus of del phi. In the vector differentiation, that is yesterday's class first problem, is similar to this. According to that, I am writing it directly. Xi bar. This n bar is similar to very first problem in the vector differentiation topic only. Xi bar plus yj bar plus zk bar. After simplifying this, we get this only for this equation of the surface. Next, we require the curl dot n bar only. This is curl, this is n bar dot product, which implies curl f bar dot n bar equal to curl is k bar dot n bar is xi bar plus yj bar plus zk bar. This is equal to just z only. Still it is not 0 only. Suppose if it is 0, we can stop here, but not 0. Next, we need to evaluate this surface integral. To evaluate the surface integral, we have to observe this surface of the object. The surface of the object is in space or on coordinate plane only. But here the surface is curved surface. This is in space. So we try to project this surface onto xy plane. To cover the total surface, of this object, we need to project this onto xy plane. If you project this onto yz plane, we can cover only this part. We cannot cover this part only. Or if you want to project this on x, this is z only. If you want to project this onto xz plane, we cannot cover the total surface only. If you project like this onto xz plane, we can cover only this part. We cannot cover this part only. So to cover the total top surface of this object, we need to project this onto xy plane only. If you project this onto xy plane, the equation on xy plane is x square plus y square equal to 1, because on xy plane z equal to 0. So on the xy plane, the region is circular region only. R is a region. It is a projection of the surface. Let R be the projection of surface S onto xy plane. Then already we have written the method of evaluation of surface integral. In that we have written the transformation surface to double only, depending on the projection only. Here surface is on xy plane. So the surface integral will be reduced to double integral. First of all, by Stokes theorem, the conversion is integral over c f bar dot dr bar equal to double integral over s curl f bar dot n bar ds. This is according to which transformation? Stokes only. But using projection, this surface will be reduced to double integral over R curl f bar dot n bar ds. So on xy plane dx dy divided by modulus of n bar dot k bar. But what is the n bar dot k bar here? N bar is xi bar plus yj bar plus zk bar. In dot k bar is z. And curl f bar dot n bar is also z. These two are same. These two get cancelled, which implies integral over C f bar dot dr bar equal to double integral over R1 dx dy. Inside the double integral function is 1. Without evaluating the integral, we write the value of this integral using the area of this given plane region. This double integral is for closed circle only. The area of the circle is given by pi r square. Therefore, integral over C f bar dot dr bar equal to pi r square, but radius is 1. Because here the equation of circle is x square plus y square equal to 1 for z equal to 0 on xy plane. So radius is 1. This is equal to pi. It is the value of the integral. Like this, we do the problems using the theorems. So finally, we have two types of integrals, line and surface integral. Normally, we can evaluate line integral by converting line integral to single integral with the help of equation of the curve. When curve is closed, we evaluate the line integral using Green's theorem or Stokes theorem depending on the object. The object is 2D, Green's theorem. The object is 3D, then Stokes theorem only. Suppose if we are given surface integral, check the surface is closed surface or open surface. If it is closed surface object, do the surface integral by Gauss divergence theorem. If it is an open surface object, then do the problem by Stokes theorem. That's it. This is about vector integration. With this problem, the vector integration topic is completed and all the subtopics of calculus are completed only. With this, the total calculus part is completed only. With this, we stop the class. So today's class is the last class for this calculus, and we close the both calculus and vector calculus are completed. All together, differential integral and vector calculus together, total topic is calculus. And this calculus part is completed. Okay. Today we stop this session because the topic is completed. And after this, you will have a doubt session. If anybody has doubt, you can ask. Otherwise, we can take rest for until next class. Okay, let us start the doubt session.
Hello.
Hello.
Good evening, sir.
Good evening. Tell me.
Sir, today's first page, sir.
Today's first
page, sir. I missed it.
Okay.
Yes, sir. I joined a little bit late.
This one.
Yes, sir. Yes, sir. Sir, this one is the first page. Previous page, sir. This one,
class.
Sir, this one.
This one on.
This one. Yes, sir. Sir, after that, sir, actually you are explaining what is the difference between the theorem, sir. Sir, actually I am little bit confused where to apply Green's theorem and where to apply Stokes theorem, sir.
Whenever line integral is given, first check the curve is closed or not. Suppose the curve is not closed, then we do the problem like this. We do the problem like this. It is general method. Page number 112F. Or like this, direct integration method. Whenever line integral is given and the curve is not closed, we do the problem like this, method 2 or method 1. It is the actual method. Okay. Suppose the curve is closed.
Yes, sir.
Line integral is given, curve is closed. Then we can evaluate that line integral using the Green's theorem or Stokes theorem. But Green's or Stokes depends on the given object. The object is 2D object. Then do the problem by Green's theorem. Suppose the object is 3D object, do the problem by Stokes theorem. It is the only difference. Total integral is given in terms of x and y. That is 2D only, with no confusion.
Okay.
Just like this problem. See this problem.
Yes, sir.
This total
Yes.
integral is in terms of x and y. So directly it is a Green's theorem. And the integral is in the form of f1 dx plus f2 dy. And next one also like this. Next one is also like this. Okay.
Yes, sir. Yes, sir.
But in that
Yes, sir.
last problem and second problem only, the region was given like this one: x square plus y square equal
last
to.
doubt, sir, today's.
Hello. Hello.
Sir, today's actually last question I could not understand, sir. Hello.
Okay. We'll go to last.
Hello.
Wait. This one.
Sir, actually, why we need to apply this that conventional method? You told us, sir, we can
Hello.
on using Stokes theorem or Gauss theorem. But why
this last problem
here we applied Stokes theorem and also we applied this.
No. You see this. This is the line integral and also closed curve. The object is 3D object here. Sphere. X square plus y square plus z square equal to 1. It is a sphere. The surface of the sphere is in space.
Yes,
So it is a 3D object.
sir.
Okay. And also the condition is there for surface. We are given only upper half of the surface above the xy plane. So it is open surface object. That is why we are using the Stokes theorem. Because of 3D object, Stokes theorem.
Yes, sir.
Okay. Now by Stokes theorem, the relation is like this: line to surface.
Okay.
To convert line to surface, on right hand side we require curl.
Yes, sir.
We are finding the curl, but curl is not 0 bar here. In the second problem, curl was 0 bar. That is why we have stopped there only, but not 0 bar. So further you have to evaluate only.
Yes, sir.
Curl f bar dot n bar is z. Still that is not 0. So still we have to evaluate this only.
Yes, sir. Z, sir.
To evaluate the surface integral, what is the method of evaluation? We convert the surface to double by using the projection. Here the object is in space, the surface is in space. That is why we are projecting the surface onto xy plane. Is it clear? Hello?
Okay. So we have to choose the suitable plane also. If the plane is not suitable, then the answer will not be correct.
Because to cover the total surface, of the object, we need to project this onto so-and-so plane only. Because for every object, the projection of the surface may not be possible on every coordinate plane only. For this object, to cover the total surface, we need to project this onto only xy plane. Suppose if we want to project this onto yz plane, we can cover only some part. We cannot cover the top, this side only. Is it clear? Hello?
Sir, the area of sir, the area of semi-sphere is not equal to the projection, that is, we are getting the circle, no, sir.
No, we are not finding the surface area.
How we are?
No, we are not finding the surface area. This is a surface. This surface integral is flux.
Okay.
It is a flux. At what rate amount of quantity flows through this cross-sectional surface?
Just we are give.
Hello.
Okay. Sir, yes, sir. Got it, sir.
Okay.
Hello. Yes, sir. Thank you, sir. Thank you.
Okay, welcome. Next. Hello.
Audible, sir.
Audible.
Sir, page number 126. Next page.
Number 126. Okay.
Sir, here why did you use pi r square for surface area, sir? It is 4 pi r square, na?
No. It is only, what is the region here? This double integral is for R. What is the R here? R is the projection of the surface of the sphere only. Surface of the semi-sphere only. This R is circular region. What is the equation of the circle? X square plus y square equal to 1. For this circle, area is pi r square, r equal to 1. Are you getting?
No, sir.
No?
I mean, you have directly taken circle equation.
Yeah,
Why
yeah.
not even
No,
the
no. Actually, in the
space
double
function?
integral, function is 1. This is same as the area of this region, area of this region only.
But region given is a sphere, na, sir.
No, no. This is the surface integral for S. Our surface line to surface is for this surface integral, but surface integral will not be evaluated directly in space. To evaluate the surface integral, what do? Again, we convert the surface integral to double integral by projecting the surface of the object onto one of the coordinate plane.
Okay.
So on the coordinate plane, we are getting only 2D plane region only. That plane region is here, circle only,
Okay.
with
Okay.
radius
Okay.
1.
Okay, sir.
So this double integral is for only R, not for S only. This is for S. But after conversion, this double integral is only for R, this R region projection only. Suppose in this double integral, it is not 1, some function is there, then it doesn't work. Directly we have to evaluate by finding the limits only. Here also, if you find the limits also, no problem, you will get same answer only. That is why without evaluating the integral, by using the limits, we get the value of the integral directly.
Okay. Okay. Okay.
It is the advantage of the double integral only.
Sir, page number 116.
116.
So your answer is 16/3, na?
16/3. Is it 16/3? The 2 to get 4, 32 minus 3. No.
I am getting 16/3, sir. So that's why I.
Okay. Check it once again. Check it whether it is correct or not. I wrote directly the answer from the options only. So you check it whether it is correct or not. This all. I will check it only. Correct answer or not. Right? Is it correct? Correct. 2 to get cancelled. 4, 3, 4, 12. 32 minus 12 by 3. Right? Correct.
Okay. Sir, why don't you take more sums on this, on the calculus part? Since this is the last lecture.
Actually, in this, we discuss about method, procedure, and models. Different models problems only. If I do the different model problems, we can do the similar model problems also by practicing.
Okay.
If I do like this, too many problems only, you require some more hours.
Right.
That is a problem only. Already I took the almost 5 plus 5, 10, 11, 22 hours.
Okay.
Actually, allocated hours are only 16 only, but I took more hours.
Okay. So then why don't you make a video on calculus only and post on that site? We will see that according to our convenience.
No, recording lecture is there already. Calculus lecture is there.
No, with more with
more
more
problems.
sums. Yeah. On
Okay.
calculus part only.
Only calculus part. Okay, we'll look into that.
Okay, sir. Thank you, sir. Thank you so much.
Hello.
Hello, good evening, sir.
Good evening. Tell me.
Sir, while starting of the multiple integral topic, sir, volume is given by double integration of the function.
Yeah, right.
And here we are taking surface integral as double integral, sir.
Surface integral as double integral. In the last problem you are talking about.
Yes, sir. Volume is also double integral and surface integral also double integral.
No. Surface integral is different. Surface integral is only integral over the surface in space.
Okay.
Double integral is the integral over the surface but that surface is on coordinate plane only.
Okay, surface integral, sir.
When surface integral and double integral both will be same whenever the surface of the object is on the coordinate plane only. If you're asked to find the integral over the some surface of the object, that surface is on the coordinate plane. In such case, surface integral, double integral, both are same only.
Okay.
Whenever the surface of the object is in space, arbitrary surface, that is the surface integral, different from double integral.
Okay, then volume, sir?
Volume integral is different again.
No, sir. Starting of the multiple integration concept, you pick double integration as volume, sir.
Yeah. In general, double integral gives volume only.
Okay.
In general, double is what is a single integral? Definite integral means area.
Area.
Like that, double integral is a volume only.
Okay. But if we do in coordinates, then it is surface integral.
Yeah.
Okay, sir. Sir, and sir, in one problem, every constant is a even function, sir. I didn't get that.
Every
constant, integration of every constant is a even function you took, sir. The integration of 3 plus x square.
Integration of 3 plus x square.
The limits are ranging from some -2 to +2.
Like
that it was.
+2.
So
okay. That is the multiple integral topic. In that multiple integral, 3 plus x square minus I think 2y dy.
Sir.
Outside dx.
Yes, sir.
Actually, inner integral is with respect to y. While integrating with respect to y, other variables as constant only. So this is a constant. This is function, right?
Yes,
so
sir.
The 3 plus x square into integral of 1 with respect to y is y. And if you substitute upper limit, lower limit, we get 2 times only. That is why we have written here. This is constant, actually constant. Constant is an even function.
Sir, how constant is every constant is even function, sir?
Every constant is even function. Let us take f of x equal to k. And how to check even function, odd function? F of minus x equal to plus f of x, even function. If I replace the x with the minus x in this function, no change. This is same as f of x. That's all.
Sir, here if it is x cube, sir?
X cube, no problem. We are integrating with respect to y. So the function 3 plus x cube is also no problem. That is a constant. While integrating the function with respect to y in the multiple integral, this is constant only.
Okay, sir.
Other variables are constants only.
Okay, sir. And 2y will be 0.
2y is 0 because y is an odd function for this function. That is, this is 0. This
Okay,
into 2 times.
Okay, got it, sir. Sir, and 95.
95.
Sir, here diagram you have wrote, right, sir? Diagram. Sir, actually that whatever the plane you are taking, no, sir, surface. The surface is
curved surface.
Yes, sir. That is 2D, sir.
No, 3D. This is a 3D object.
Means it's like sphere.
Not sphere. Any surface, any object in space, arbitrary surface.
Okay, sir. For
not exactly a sphere. Not sphere. Any object. 3D object.
For surface, how we can draw this, sir? A tangent.
No, actually, for the surface, at a particular point, if we draw the plane, if any plane touches the surface at a single point, if a plane touches the surface at a single point, such a plane is the tangent plane to that surface.
Okay.
At that point, right?
Perpendicular for that surface is normal, sir.
Normal. But on this tangent plane, we have taken the dr bar. Dr bar is one vector, and perpendicular to this dr bar is normal only.
Okay.
Because it is already on the tangent plane only.
Okay, sir. Got it, sir. Sir, and 161, sir. 61.
Only 61 or 161?
161.
161 is not there, I think. 126 is the last.
Oh, I thought I returned the wrong, sir. Sir, actually, I wanted to ask that unit normal vector, sir. I'm
Okay.
getting confused. What is unit normal vector?
Unit normal vector is for surface, if you find the gradient, that is a normal vector.
Okay.
And if you divide any vector with its length or magnitude, the resulting is a unit vector.
Okay, okay, sir.
The vector with the unit length is the unit vector.
Okay, okay, sir. Sir, 112.
1, 1, 2.
Sir, actually, I'm getting doubt like integral and normal integral both are same, sir. Line integral and normal integral.
No, no, just like a surface integral. Surface integral, double integrals are different. When these two are same means the object surface is on coordinate plane. Like that here, line integral is different from these ordinary definite integral. These two will be same whenever the curve is along the x-axis or y-axis or z-axis. The given curve is, the arbitrary curve is along the x-axis, y-axis, z-axis, line integral, single integral, both will be same only. Suppose the curve is in space, arbitrary curve in space, then line integral is different from ordinary definite integral.
Okay, 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 sir.
Suppose if you take one dimensional motion, the object can move either right direction or left direction.
Left direction.
So only linear motion, that is, right?
So
That
they're
is along the
ordinary
x-axis directly. In such case, line integral, ordinary, definite integral, both will be same.
Okay, but in the space,
Different only. Suppose the object, that path of the moving object is in space.
yes, sir.
That is arbitrary path that may travel in any direction.
Okay.
So that is the line integral, space integral.
Their vectors come into pictures.
Yeah.
Okay, okay. Sir, and 112. Okay, 112. Sir, here you took only the limits for x, sir. We can take y limits also, sir.
Anyone we can take. Whatever you choose, x equal to 4t, y equal to 2 minus t, z equal to 1 minus t, we get same limits only. That is why out of 3, we choose a simple equation.
No, sir. At t equal to 0 to 1, you took, right, sir? From the 2 to 1 also I can take, sir.
No. 2 to 1 means if you take the y equal to 2 minus t. Here x limits are 0 to 4 means the x limits are the same as the x coordinates of the points.
Okay.
Suppose if you take y equal to 2 minus t.
Okay, okay.
Instead of x equal to 4t, if you take y equal to 2 minus t for finding the t limits, in such case you should take the 2 to 1 y coordinates.
Okay, okay, sir. Got it, sir. Sir, and 118.
118.
Sir, actually, irrotational is for curl, sir. But here you are taking for gradient.
No, every gradient is irrotational. Curl of gradient is 0 bar. Every gradient is irrotational. Randomly choose some scalar field. Find the gradient, that is vector field. For such vector field, if you find the curl, then that is always 0 bar, irrotational.
Okay.
From this we say that every gradient is irrotational. So gradient is vector. If I write this as f bar, what do you get here? F bar equal to del phi or not?
Yes, sir. If del phi is equal to 0, then it is solenoidal.
Yeah.
Okay.
No, what is it? Del phi?
Del phi equal to 0.
No, not del phi. Del dot f bar. Del dot f bar equal to 0, that is solenoidal.
Okay.
Del cross f bar equal to 0, irrotational.
Irrotational. Okay, okay. And sir, 122, sir.
Okay. 122.
Okay, okay, I got it, sir. Actually, here I was having doubt like, not this one, sir. In one problem, at middle only we got the integration, volume integral 0, right, sir?
Yeah.
So after that, how I was not getting, sir. But one example is solved with that problem also, sir. That I got it, sir. 123, sir. Not 123. 125, sir. 125.
Okay.
Sir, actually, if we are considering here, if they give sphere means hollow or solid sphere, sir.
This is sphere means hello.
Divergence is for a hollow sphere only, sir.
Not like that. Here, first of all, sphere means only this surface. We are talking about surface.
Okay.
We are taking the surface of sphere means only the top surface only, the upper part, upper portion of that object.
Okay.
V. If you take V means inside the.
Okay, sir.
For a solid sphere, volume V means inside this. The top of the object is the surface only, top portion.
Okay.
That the surface
Okay,
S encloses the volume region V only.
V.
So inside portion is the solid object is the V only. Outside the outer is the surface only.
Okay, sir.
Got it?
And sir, if the Z is 0, then we need to apply that Stokes theorem, sir.
Z equal to 0, directly we apply the Green's theorem for closed curve.
If it is not 0, then we will apply Stokes theorem, sir.
Yeah.
Okay. We need
If you
to
are
check
given only the region on XY plane, Green's
Okay.
theorem. If you are given region in space, that is 3D object, then Stokes theorem.
Okay, sir. And sir, while we are studying electromagnetics, sir, Green's theorem is not there, sir.
I think you are not using that one. You are using Stokes theorem and Gauss.
Stokes theorem, yes, sir.
Because there you are finding the 3D objects only.
Okay.
If you find 2D object, then we can use that also.
Green's theorem. And sir, last doubt, sir, 126. Sir, here third step, sir. Dx dy divided by how we got that, sir? N cap into n bar into k.
That is transformation. I wrote that note point in the method of evaluation of surface integral.
Okay.
We have taken the projection of the surface onto XY plane. Because of the XY plane surface, in place of ds, we write this only. In the surface integral, we have written this only. This is surface integral. Next page is this. We have written like.
Okay, the right side diagram. Okay, sir.
Based on the projection, we take the one of the relation only.
Okay, sir.
Okay.
Sir, and one more doubt, sir. Sir, open surface and plane both are same, sir.
Surface means that may be curved surface or plane surface only.
No, sir. If the surface is plane and the surface is open.
Open surface. Open surface. Suppose if I take this some sheet, plain sheet. Plain sheet is the two-sided open surface, because we are able to see the top surface, bottom surface, both surfaces.
So that is open surface.
Open surface.
And if you take cup, also open surface.
Open surface.
If you take ball, then it is a closed surface.
Closed surface. That because the top surface is enclosing some space region inside this.
Okay.
In such case, we are unable to see the inner surface, and we are able to see only outer surface.
Outer surface, okay.
For any object, if you are able to see the inner and outer, then that is an open two-sided surface.
Okay. And sir, in one problem, cuboid problem, sir, today.
6 faces were given.
Yes,
cuboid is a closed surface.
Sir, there you said one point, when it will be open, sir.
Out of 6 faces of that cuboid, if you are given only 5 faces, one face is not given, then that will be open.
Okay, then height will be reduced like that, sir.
Yeah. Or any one of the faces is not given. Out of 6 faces, one face is not given.
Okay, sir.
If you are given boundary of that and over surface, then you have to go for Stokes theorem.
Okay. Sir, actually, thank you, sir. Because in electromagnetics, I was unable to understand some vectors things, sir.
Okay.
So here I was confirmed, like I got understood.
These are the basics for the topic only.
Yes, sir. There I was feeling some difficulty, sir. Here I understood clearly, sir. Thank you, sir.
Okay, right. Welcome. Hello.
Hello, sir. My doubt is cleared, sir.
Okay. Hello.
Hello, sir.
Ah,
Good
tell
evening.
me. Good evening.
Sir, in 123,
123. Hmm.
I'm just asking that the surface is x square plus y square is equal to 4. It's a 2D surface, no?
No, no, no. Actually, where it is on the z equal to 2 plane.
Okay, sir.
Here, object is the intersection of x square plus y square equal to 4 and z equal to 2.
Okay.
Hmm.
If it was z equal to 0, then we would have applied Green's theorem.
Yeah.
Okay.
Because that will be on xy plane directly.
Okay. Sir, one more thing. Just if I have any further doubt, can I ask you on WhatsApp
Oh, yeah.
afterwards?
We can ask.
Okay. Thank you, sir. Done, sir.
Hello.
Done, sir.
Okay.
Hello.
Hello. Tell me.
Good evening, sir.
Good evening.
So, the page number 112, 112.
112. Okay. Is
Yes,
it?
sir. So, yes, sir, this one. So, here, the almost the last step, I is equal to from t to 0 to 1. So, how did we get 2 minus 4t dt, and at that step I could not understand, sir.
This one, just below the green box.
Yeah, yes, sir.
Oh.
Yes, sir.
Actually, what is our
minus
main
4t.
integral? Main integral, top, go to the top. From the top, second step. I equal to integral point to point inside the integral 2z dx. What is the z
Yes,
here? Z equal to 1 minus 2t
1 minus 2t.
into 2. 2 minus 4t. That was I wrote here.
1 okay. 1 minus, okay, sir. And sir, then yes, sir, got it, sir. So, and the next one, the next question, the second one,
This one.
the next one,
Is it?
the direct integration. Yes, sir. Yes, sir. So here, on basis of what have you separated it, sir? The next, the second
Just
line.
by observation of the terms only. By
Like
observation of
2xy dx.
Actually, here the name of the curve is not given. Equation of the curve is not given. That is why we cannot evaluate directly only. So in this case, we should check the function is irrotational or not. But without checking irrotational or not, if you check the irrotational, it will take some more time only. So without checking irrotational, just observe all the terms in the integral. By observation, if you are able to write all the terms as single term like this, differential of some function, we can go for direct integration. If you are able to write the sum of the three terms as a single term like this also, indirectly we can set the function is irrotational. Whenever function is irrotational, this exact differential is possible, otherwise not possible only.
Okay.
And like this, we have written the many formula in the differential equation topic only. Have attended differential equation?
No, sir. Calculus is my first class.
Okay. Oh, you do one thing. You take the differential equation class notes from friends or already.
I'll watch the recorded videos of yours, sir.
Okay.
Okay. I'll see through this, sir. Thank you, sir.
Okay. Okay, and closing the doubt session also.